Alright, in this video we'll be looking at some example problems from our 13.1 MyHrw. Number 1 says, what does the value of f of x equal? And we have the function 1 plus 1 over x to the x power. It would seem that if we keep putting larger powers in here, that this would get bigger and bigger and bigger without bound, but it turns out it does not. And this is this function tends towards this number e. And E, also called Euler's number. Hopefully you watched the video where the gentleman showed a lot of values, a lot of places that E occurs. It's approximately 2.71828, and it goes on and on forever with no end. It's a lot like pi in that regard, and that's what this thing is going to tend to. So let's look at Desmos and we'll see that. Here's the function 1 plus 1 over x to the x power. I'm looking at just the positive end. You can see it flattens out. It's asymptotic, we say, and you're going to see that the y values are getting closer and closer to that 2.71 number. If I zoom out, you could see even further, 2.715, so forth and so on. So on number 1 here, as x tends to positive infinity, as x tends to positive infinity, f of x tends to this value e, and that number right there. Alright, now number 7. The graph of f of x equals c times e to the x crosses the y-axis at 0, c, where c is some constant. Where does the graph of f of x equal f of x minus d cross the y-axis? Well, this is a y change, and so we're just going to change the y coordinate that much. It's going to cross at, used to cross at c. Now it's going to cross at c minus d. The y changes happen like we think they should, and we'll look at a concrete example of this. So graphing our original function, f of x, c times e to the power of x. And we can see that in this case c is 1, and that's where we're crossing over the y-axis, 0, 1, because if we substitute 0 in place of x, e to the 0 is 1, and c times that would be 1. Now, placing a new function in, we'll call this new function g of x, and we're going to do our f function. That's what it's telling us to do, minus some value d. Add a slider for d. You'll notice that whatever we make d, that's going to be the distance between those 2 points. In this case, it's 1, because that's what d is. If we made d 4, well, our new crossover here is at 0, -3. The original one was at 0, 1. You can see it went from 1 to -3. That's a subtraction of 4. This is a y change. Y changes happen like we think they do. Subtract 4 moves it down 4. So it crosses the y-axis at the point 0, c minus whatever that value d is. Now we're looking at number 9. Given a function of this form, identify the reference points and use them to draw a graph. Select the graph below that matches the graph you have shown. Alright, well, these are our original points in our parent function. F of x is equal e to the x. We have these points. 0 would pair with 1. Clearly, if we substitute 0, anything to the 0 is 1. 1 is going to pair with e. That makes sense too. If we substitute 1 in here, we have e to the first. Well, we're going to make some changes. Okay, and our new changes are this new function. Our new function is g of x is equal to negative e. I'm going to put a -1 out there just so we clearly see what we got going on. E x plus 1 minus 3. Well, let's consider what our changes are. This negative 1, that's a y change. And this minus 3 is a y change. This plus 1 is an x change. And we know inside inverse. Okay, so what's going to happen with our x? We're going to subtract 1 because it's adding 1. Subtract 1 from our x. What's going to happen with our y? We're going to multiply by negative 1 and subtract 3. So the y change, our new y, which I'll call y prime, is going to be negative 1 times old y, subtract 3. We're multiplying by negative 1, we're subtracting 3. The x change, our new x, I'll call x prime, is just going to be our old x minus 1. We know that the x change happens opposite of the way we'll think. So this new point 0, 1, well, the x change is just a subtraction of 1. 0 is going to become negative 1. Our y change, we're going to multiply it by negative. We're going to multiply this y value by negative 1, and we're going to subtract 3. 1 times negative 1 is a negative 1, minus 3 is a negative 4. Okay? All right. This new point. 1, well, 1 minus 1 is 0. The y change, we're going to multiply by negative 1, so that would be negative e minus 3. And you could use a calculator to estimate those. Negative e minus 3. It's going to be negative 5 point something. And let's look at Desmos to see this. All right, we got e to the x, that's our f of x. And then now in our g function, our g function is going to be negative e to the power of x plus 1 up there in that exponent. And, whoops, we need to begin the exponent with that. Plus, we're going to group our exponent in parentheses so we can get that plus 1 up there with it. And then out of our parentheses, we've got minus 1 that are minus 3, forgive me. Minus 3. All right. So we see that 0 pairs with negative 5.718. That is indeed 0 negative e minus that, because negative e would be a negative 2.718 minus 3 would be that negative 5.78. We know that we believe that negative 1 will pair with negative 4. Looking at our Desmos, negative 1, we see it will indeed pair with negative 4. All right, so the domain is still all reals. We can put any number we want in there for x. The range, just take a look at your graph, and you can see we're asymptotic right here, and then all of the rest of our y value is going to be less than that. Originally, our asymptote is at 0, and this asymptote is our asymptote is an x value. It's that x change, so our new asymptote is going to occur at this value of negative 3. So the range is going to be y less than negative 3. Domain's going to be all reals. With this number 9, you should be able to then to work with this number 9. You should be able to do 9, 11, and 13. They are all deal with those transformations. Give those a shot. I'm going to skip 15 for a second and go on and look at 17, 19, and 21. They're pretty similar. So let's take a look at number 17. All right. Number 17, we have this function, p of t equals. P of t is just the output. It's some final number of caribou or whatever it is that we're looking at, a population sometime t. This p naught is some initial value. E is our number e, 0.154 to the t power. I want to talk that this really is just our standard form of our exponential. Y equals a times b to the x power. Y, this is our output, that's p of t. A is some initial value, that's p naught, that's our initial population. B, the base of our exponential, we have this particular number that is our base, that's e now. And here x is our input, here our input is t. These two forms are very similar. All right. Number one says the herd will reach 23 million when t is approximately what? So that's our population is 23 million. Our P naught is from 1954, that's 4,700. It's a big increase in our caribou. Is equal to, forgive me, 4,700 times e to the 0.154 t. One way we can solve this is simply graph one side in y1 and graph the other side in y2, and we can see where they intersect. Let's take a look at that. $27 million. We have to zoom out a lot on this one, aren't we? And then the other one is 4,700 times e to the power of 0.154. 0.154x. All right. No longer need that. Now we're just going to zoom out until 27 million is going to be way up there. Looking for a horizontal red line. There it is. All right. And we're looking for that point of intersection. That's 27 million, 2.7 times 10 to the 7th. And this 5.61 times 10 to the 1st, well, 10 to the 1st is just 10, so that's just moving that over one decimal. That's 56 years. And 56 years, if we substitute 56 into this, we would have that. And in 56 years, our caribou is going to go from 4,700 to 27 million. Pretty incredible. So when time is 56, rounding it to the nearest year, 56.2 would be 56 years. It'll reach 23 million 56 years after 1954. 1954 plus 56 years, that's 2010. So after 1984, subtracting 1984, looks like 26 would be here. The year is 2010. 56 years. Now we need to find our growth rate in a percent. Well, from the step-by-step or the example, it tells you that the growth rate R is going to be equal to 1 plus R is going to equal to e to the c power. What is e to the c power? Well, that's simply this quantity right here, e to the 1.54. We're not talking about our input variable. We just want this factor. It is this base essentially of our exponential. So in our particular case, we want to solve for R. 1 plus R is going to equal e to the 0.154. All right. Evaluating e to the 0.154. E to the power of 0.154. And we know it's going to be less than, that's like taking a root of it. We get 1.166. So this is 1 plus r is approximately 1.166. While solving for r, we'll subtract 1 on both sides. So r is approximately 0.166, and we'll convert that to a percentage by moving it over 2 decimal places. This is 16.6%. It says to the nearest tenth of percent, so might be 0.6, might be 0.7. I noticed mine was very close to 0.5. The next digit was like 49. So that 49 there, this very easily could be a 7 there. So just be sensitive that we're rounding to this decimal place. That concludes this video.